My name is Eric Nichols, and I call sign KL7AJ. Live in Fairbanks, Alaska. Been there for about 47 years. I've been a ham for 52 years, and I've worked with Gordon West for about half of that time, helping do the instruction books, and also I'm on the what they call a question pool committee. So kind of a poetic justice after suffering under the FCC licensing for so many years. I now get to impose some torture myself. So I am involved in writing some of the new questions. So the new FCC rule question pool is just came out, and the W5YI books, which is now under the auspices of ARRL, is also coming out very soon. Anyway, this is probably a little bit different topic than we've had here, because most of you learn this stuff to get your license and never use it again. So I promise you that everything you've ever learned in ham radio training and high school arithmetic will come back to haunt you here. Anyway, I'm going to talk about some relatively, I think it's original with me. I've been teaching electronics for many, many years now, and we have some of the same problems that keep coming up and over again in trying to get people to understand how to do some basic not only troubleshooting, but circuit analysis, how to figure out circuit problems. So I'm going to talk a little bit about this, which is make it as simple and easy as possible. Designing electronic circuits can be fun and easy with the right systematic approach. However, many hams and even electronics professionals aren't exactly sure where to begin when designing or modifying a practical electrical circuit. We'll present a unique and memorable method for attacking any electrical circuit problem, which I call the PIER review method. And this is a play on words. It's not PEER, it's PIER. And this stands for power, current, which is I, voltage, and resistance. We apply this method to a simple design problem, and then we can apply it to any circuit whatsoever. So, 2 laws for using peer review. And number one, there are really only 2 relationships we work for solving an electronic problem. And who knows what the primary rule in all electronics is? Ohm's law, right? And then we have a variation of that, which is the power formula, which is as easy as pi, which is power is voltage times current. So these are the only 2 laws that we're actually going to be using to solve a problem. So we're going to use an imaginary problem, but it's also going to be a practical problem. So let's say you're on a desert island with a 120 volt generator. Then again, maybe you probably aren't going to have a 120 volt generator on desert island. But we have 120 volts, 60 hertz AC, which is what we all have coming out of our wall sockets in the US here. And we have a 12 volt light bulb. And I use a 12 volt 25 watt light bulb because this is a typical tail light for a car incandescent light, unless you go into all LEDs, but very, very common bulb, 12 volts, 25 watts. And we want to be able to run this from 120 volt outlet. Now this class here is very interactive. I am what I call a Socratic teacher. I don't sit up here and pontificate. I get the answers from the audience. So if you ask you questions, feel free to chime right in at any time. So one way we could make this bulb happy is to use a series dropping resistor, right? We could just put a resistor in series with the lamp, which will drop the lamp down if we have the right value resistance to 12 volts. Any disadvantages of this? What would be a reason you would not want to do this? Lots of power, okay? And if somebody wants to, everybody have your calculators out. I'll let some of you here calculate how much power will drop, but we'll come back to that later. And you don't happen to have a step-down transformer that's going to do the right job for you. So we have one other thing available, or a couple other things available. We could put in a series capacitor, or we could put in a series inductor. Either one of them would be drop our voltage down very efficiently without any losses. So here's our circuit in question here. As you see, we only have 3 components. We have a generator, which is 120 volts AC at 60 hertz. We have a capacitor, which is the unknown value. We don't know what value that is. That's the point of this problem here. And then we have our lamp here, designated DS. And I don't know why they always use DS for designating lamps in schematics, but we'll be consistent with that. And it's 25 watts and 12 volts. So the process, what we do here, which may seem to be a lot of overkill, is we put together a little table that shows everything we know about every component in the circuit. Now the reason we do this is number one is it gives us immediate sanity check because we have two ways of solving any problem. The other thing it does is it suggests several ways of solving any problem. So there's always going to be more than one way of solving a problem. And by doing it several different ways, we may not necessarily come up with the fastest way right off the bat, but we'll always come up with something that works if we follow this procedure here. So we build a little table for each component. Each table has 4 columns: power, P, current, I, voltage, E, and resistance. Now resistance can be either an impedance or a pure resistance. Now, what's Ohm's law if we have a complex impedance? What is it? Anybody know? Okay. If it's just pure resistance, it's E equals I times R. If it's got a complex impedance, it's E equals I times Z. So we simply replace the R with a Z, and we now can work with the problem here. So the process is we build a little chart or a little table for every component. And again, TMI, too much information? No. This may seem a bit tedious, but especially for such a simple circuit, but there's a method to this madness. And the process of logging the P, I, E, and R for each component will suggest at least several ways of solving the problem. So what we're going to do is we're always going to go around the loop here the same way. Rather than anticipating, well, let's guess ahead of what this may be. We'll do it very systematically, so we won't take any shortcuts. So this is going to take a little longer than you may be used to. Some of you could almost do this in your head, but we want to be able to have a process which we can apply to any circuit at all. And again, feel free to interrupt me at any time. Just yell right out. A little bit noisy here with that, but if you have any questions here, we'll fill that out. So what we'll do is we'll figure out, we'll put together our table for V1. V1 is our voltage source, so if we want to go back here, we can go to this question here. So V1 is our voltage source here. And what we'll do is we'll put a little table there. And the table is, okay, what's the power at V1? We don't know, okay? So feel free to put a question mark there. Do we know the current? Not yet. Do we know the voltage? Yes, okay, that's given. And do we know the resistance? Now, why I put a 0 in here. Why do we use a 0 here for the resistance in the voltage source? Well, in electrical engineering, that's assumed to be the case. A voltage source, by definition, has 0 internal impedance. As a matter of fact, any voltage source that has no impedance has the capability of supplying an infinite amount of power. It's only the internal resistance of a power supply that gives us any limitation on how much power we can crank out. So we have this table here built up for V1. We have our capacitor, which is next in line, and what do we know about that? Well, we know the power is going to be 0 because an inductive or a reactive component does not consume any power, right? It stores energy. Capacitor stores energy. If it's a good capacitor, it doesn't heat up at all. Now, we always assume that we have perfect components when we're ever doing something like this. Oh, okay. We always assume we have perfect components if we're doing something of this, so we can be sure that, well, if the problem becomes solvable, it doesn't become too complicated. Do we know the current yet? No, we don't know the current yet. Do we know the voltage? No, we don't know the voltage yet. And do we know the resistance? Well, we do know that there's going to be no internal resistance, again, because it's a perfect capacitor or an ideal capacitor. But we don't know what the reactance is going to be. So we have to figure that out later. So that we know very little about what's in C1. Now we have the lamp itself. And the lamp itself, we have the most information, right? We're given the power, which is 25 watts. We don't know the current. We know the voltage. And we don't know the resistance. But we have two pieces of vital information. So at this point, what we know the most about is the lamp. So now we'll go around the loop again, and we're back up to the V1 table. And so now, do we know the power of V1? And I put 25 watts. Why do we know that? Conservation of energy, right? If we have 25 watts consumed, and the lamp is the only thing consuming any power, that means our generator has to be putting out the same amount of power. So we can fill in that blank. Do we know the current at this point? No, we do not. Do we know the voltage? Yes, it's still 120 volts, and again, the resistance is 0. Go around the loop again. Next time, we go to our C1, and do we know the power? Still no power. Do we know the current? Nope. Do we know the voltage? Nope. Nope. We can't just subtract it because it's a reactive circuit. If it were a resistor, we could just do that, but we can't do that in a reactive circuit. And now we have an X value of X of some value, but we don't have enough information there yet at all. So now we step around to the next component, which is our lamp again. So we have our power, and we're given our voltage. So I wrote 2.08 amps. Where did that come from? Okay, I is, well, P is I times E, right? So if we want to get I, it's simply E over P. So it's 12 over, it's P over E. So it's 25 over 12, which comes out to be 2.08. And feel free to break out your calculators if there's too much. How about the resistance? Yeah, E equals I times R. So R is E over I. So E is 12 over 2.08, which comes out to be 5.77 ohms. Okay? So we have two more pieces of information, and we've completely filled out our table for our lamp here. Back around again into our voltage source. We know the power, right? Because that's going to be equal to the power they're consuming in the lamp. We know the current. Why do we know the current? It's a single loop, so the current's going to be same everywhere. So we're going to say, in every component, we're going to have the same current there. We have the voltage that's given, and again, the internal resistance is 0. And now we're back to something here. Now, let's go back here again. As you see, we now have the entire V1 table filled out. But now the fun has just begun. We now need to reconcile something. What total circuit impedance will allow 2.08 amps to flow when 120 volts is applied? So we have to look at the complete impedance of the circuit. And again, by using Ohm's law for impedance, is that Z is E over, or I times Z. But we don't know what Z is. So we can rearrange this formula, so Z is equal to E over I. What is our E in this case? 120 volts. What is our I? 2.08. So now we can come up with a value for Z. And here we have it. Now, why are we coming up with Z squared? We go back to Pythagorean theorem. Okay, who wants to just yell out what the Pythagorean theorem is? Okay, so the hypotenuse in a complex circuit is Z, which is our total impedance. And so Z squared is equal to R squared plus X squared. Okay? So we know that Z squared is 3329 ohms because we're going back to what our Z was, and which is actually comes out to be, where would you go here? 57.7 ohms, okay? Our Z is 57.7 ohms. Now, we square that to get Z squared. And why do we need Z squared? Well, that's so we can fit it back into our Pythagorean theorem. So Z squared is 329 ohms. R squared. Now, what is the R we're using? What value of R are we using? The only R in there is the resistance of the lamp, which was, going back here, 5.77 ohms, okay? So now we can square that. So we have 3329, which is a total Z squared. We have R squared, which is 33.29. We subtract them, and now we have this 3296. Now what is 3296? That's X squared. And what is X? That's our reactance of our capacitor, okay? So see why if you want to keep track of all of this, so we're going to keep going back and referring to this. So we aren't quite out of the woods yet. We need to know the actual value of C1, not just its reactance. Now, what's the formula for capacitive reactance? Anybody got it in your head here? Okay. Recall that capacitor reactance is 1 over 2 pi times Fc, where C is capacitor. So what we need, we know what our X sub C is, right? So we need to go back and we need to find C. So what we need to do is solve for C. And we can do this because we have everything we need to know. We have the frequency, which is 60 hertz. We have X sub C, which is 57.4. And you can either use your memory calculator. I've done this calculation already. So it comes out to be 46.2 microfarads is the capacitor we put in there. So we could put a 46.2 microfarad capacitor in series with our lamp, and our lamp's going to be perfectly happy. It's not going to evaporate. Right? So isn't that a fun way of doing that? Now you say, well, boy, this is a really complicated circuit to do something. But there's only 3 components in here. But when we start working with reactance, there's no shortcut. We just can't take 2 resistors in series and say one's just subtract one for the other. If we were to replace that with a resistor, yes, that would be true. What we could do is we simply subtract the 12 volts from the 120 volts, come out with 108 volts, and then we can figure that's our voltage across our dropping resistor. But it doesn't work that way. So again, this is bringing back, this used to be on the advanced class license. Since anybody here have an advanced class license? An old timer. It was definitely on that, and it's certainly going to be on the extra. It was maybe glanced at in the general. Now I don't remember. I took my general back in '72, so I'm trying to remember. Does anybody remember who took a general class license in the last 20 years or so, whether it had the full complex impedance formula? You didn't? Okay. Okay, so it was only. Anyway, this is very practical stuff because we're going to use it all the time. Now, I'm going to go into another topic which is really related to that, and we'll go back to what we call the sanity check. So, if you insert a 46.2 microfarad capacitor in series with a 12-volt lamp, you can plug it right into 120 volts AC, and everything will work just fine. Just make sure your capacitor is rated for AC. Not all capacitors are good with that. Now, I wouldn't recommend actually using this circuit, but it's a good demonstration circuit. Now, we've already finished our problem. We've come up with our final answer, but let's continue further and show the neat thing about this peer review process. So we'll go back to C1, and now we have some more information. We know the power, again, is nothing. We know the I is 2.08 amps because, again, the current's going to be the same everywhere in the circuit. The E is 119.4. And how do we do that? Well, in this case, we can figure that out because we can use the reactance formula. E equals I times X. Okay? So we can just substitute the X for what we would have as resistance. And when we come out with a voltage across here of 119.4 volts. And we also come out with a reactance of 57.4, which we already calculated earlier. Well, let's show you. Yeah, the voltage won't be the same, but we'll show you why. Now, here's where we get to the sanity check. Let's for the moment say that immediately after figuring out the circuit current of 2.08 amps, we decided to determine the source power by multiplying our voltage 120 by said current. So what's 120 by 2.08? What's that? Okay. 249.6 watts. Now, do we see a problem here? What unit is this when we multiply simply voltage by current without taking in consideration any phase shift? It's volt amperes, right? It's not watts, it's volt amperes, okay? So what we want to do here is we want to reconcile this. So we'll come around this problem a different way here. So we got 249.6 volt amperes, which is obviously very different from the 25 real watts that we've done. And so what is this? Well, this is our apparent power. Well, how do we get from apparent power to real power? Well, again, since we want to use several different ways of working with the problem, let's work backwards. So how do we figure out the phase angle of a circuit that has both resistance and reactance? Anybody remember the formula for that? It is on the general class commercial license. Okay, it's the arctangent of reactance over resistance. Everybody have their calculator out? So what is our total reactance in this circuit? We've already figured that out, right? 57.4 ohms, okay? And what's our resistance? 5.77. And so now you take the arctangent, and tangent on your calculator, if you go to the trig functions and put the inverse, it's the inverse tangent. That's what arc means. So it's the inverse tangent. And so the inverse tangent of 57.4 over 5.77 is 84.3 degrees, almost a 90-degree phase shift, okay? Now, we have one other step to go. How do we get from real power to true power? Well, the formula for that, and the people who really work with this a lot are the power line people, the power distribution people, because they're always working with the volt amperes and that sort of thing. So what we do is we take our volt amperes and we multiply that by the cosine of the phase angle. So who's got their calculator? What's the cosine of 84.3? Good man, up front. about 0.099, which is our power factor. So now we multiply our apparent factor by our 0.099, and we come out to 24.7 watts. Okay, pretty close to the real answer. Now, we do not have exactly right, because we've dropped a couple of decimal places in the calculations here, which brings me up to my entire next topic here, with something which has been largely ignored in both commercial and amateur use here. So I've written a whole postscript to theirs, and this may be actually more of the topic. So how many of you have had formal electronics training, either in high school or whatever? Okay. Now, what number do you use for pi? Okay, when I teach it, inevitably somebody will come up and say to me, Professor, should I use 3.14159 for pi or 3.1416? What do I tell them? 3.1. Why? How many significant digits are in a standard resistor? Two significant digits, right? Now there's some precision resistors out, but that's old school guys, you know. Your standard resistor had two precision, and if you got a capacitor, how many significant digits are in like a mica capacitor? Two significant digits. Why do we go to 6 significant digits for pi if the most accurate component we have is 2 significant digits? So if we use 3.1, it's going to be more than accurate for anything that we're going to be doing in electronics. If you've been around electronics at all, we know that your standard resistor doesn't have a fourth stripe as a 20%. That's plus or minus 20%. And most radio circuits will work just fine with a 20% tolerance. Now, where do we want high precision? Where would we need something more than 20% tolerance? Well, not necessarily, but measurement, okay? Anytime we're using instrumentation, your tester instruments, you want to be at least 10 times as accurate as whatever you're measuring. So if you want to measure the accuracy of a 5% resistor, you want a 0.5% tolerance in your instrument. Another thing is any frequency determining components, like an oscillator or anything like that. We want to have really high precision components. Now, if anybody here ever had to build a VFO from scratch, any old timers here? Why can't you just look up your tables there for the components that you design and plug them in there and the thing's going to work? Well, same thing you thought. The tolerances that we need are far more than what you can get for standard components. So you always got some adjustable capacitors and everything, right? Doesn't matter whether you've got we were talking at the last lecture that was here, the tuned loop antennas, it's got the big monster capacitors in there. It'd be great if you just put a fixed capacitor. It'd be a whole lot cheaper than a variable capacitor, but you just can't get that kind of accuracy with fixed components. So to make things practical to build, we have to put some trimmers in there. We have to put adjustable devices in there. If you've ever worked with old VFOs before synthesizers came out, one of the biggest problems was the temperature stabilization. Anybody heard the term the Swan Drifty 250? There's a 6-meter rig there that was famous for drifting across the entire band there between turning it on and warming it up. So there's all sorts of temperature compensation devices that were used on there. Special capacitor that's hopefully drifted the same or the opposite direction of everything else. And if you're really lucky and spend a lot of time, you could compensate it. So anyway, Collins radio was one of the first ones to really solve the drift problem when they went called permeability tuning. Rather than a variable capacitor, they had ferrite slugs that were tuned in and out. So a lot of these problems have gone away with frequency synthesis. But somewhere you've got a crystal oscillator operating which is synchronizing all this. So it doesn't matter how sophisticated your digital circuitry, even your microprocessor, it's got a crystal in there which is very precisely tuned. And you can only grind a crystal so accurately, but you're still going to have to trim it there. So this is one of these cases where you're going to need more than 2 significant digits of accuracy. And of course, if you're running an atomic clock or GPS or anything, you can have many, many more decimal places than you work with here. Now, if you're doing a long problem and you have to use pi or some unit in the middle of the process, we want to maintain our accuracy without losing it by doing round-off errors. And I showed you in the problem we did, we actually had a small error because we were doing some rounding off. What we could do is we could keep that symbol until the very end. For example, rather than putting 3.14 or 159 or whatever, we just use the symbol pi because pi has an absolute value. And then we can plug that in at the very end of the problem and we say, okay, here we have pi. We know what pi is. It's not going to drift. So then we can plug the pi back into the program at the end, and that'll come up with our very precise answer. So using a symbol pi in the middle of a formula is perfectly good. You don't have to resolve it at every point in between. So how many here are physics majors or did major in physics? Not too many geeks here. Okay. Let's see here. I think a small thing about standard value components. Anybody done any filter design, like out of the AWL handbook for low-pass filters or anything? Yeah. You work with LC? Yeah. And the LC has the subcategory of SVC capacitors, which are standard value capacitors, so you don't have to do all the trimming. You can come up with a filter design that's pretty standard with those SVC capacitors, which normally if you put it together, you don't have to do too much trimming at the end. And so that's one case where a very well-designed circuit won't be touchy like that. So we can design very good low-pass filters without having to do trim them in the field. I noticed one of the tents out there in the field in the flea market there had this filter. It was a low-pass filter. It was about 1.5 feet long, and it had about 15 tweakers on it. And they're all tweaked by the front end. And I can imagine they're running that thing out in the field there and adjusting this low-pass filter with a screwdriver on the fly. So that's the way things used to have to be done. I used to work in TV broadcasting, and we used to have to adjust those kind of filters like that. Fortunately, with the SVC and these great tools like LC is an absolutely amazing tool, especially if you've had to design filters the hard way before you had that. So the computer modeling is excellent. Anybody here work with PSpice or any other spice programming? Yeah, great program, isn't it? There's other couple of programs I like even better than PSpice. LT Spice is kind of the standard, which is, I think most of the AWL literature goes with LT Spice. There's another program out there called ICAP4, which is amazing because what you can do is it's programmed the same way as SPICE programs are, but then you can take any component in there and you can sweep the value. So you say, well, I'm not sure if this is right if you're building a bandpass filter, and you can pick a component in there and it will optimize it so you'll find exactly the right component you want. So it's a great program. So if you haven't played around with SPICE modeling, it's really a lot of fun. A lot of similarities to antenna modeling. Who does antenna modeling here? Yeah. So a lot of similarities between circuit modeling and antenna modeling, and it's a good reality check. You never want to turn over your brain to a computer. So most of the people who appreciate antenna modeling the most or those of us that have done it the hard way for a long time and said, wow, this certainly takes a lot of work out. Well, you need to kind of know what the answer is going to be before you hand it to a computer, because computers don't have much common sense. So you can have totally unusable solutions, whether it's with a circuit or an antenna. So you want to have a pretty good idea what it's supposed to look like, and that only comes with experience. You know, you have a dipole, okay, I know what the radiation pattern of a dipole kind of looks like, and if I do an antenna model, it comes out completely different. We know I either model it wrong or something's out of whack. So computer modeling should always be a iterative process between both, you know, practical field work and the modeling itself. So any particular questions on this particular problem I did? Did it all make sense? You were out in a desert island and you had to figure out how to light a light bulb without frying it. You do. Now let me throw a little kink in here. Let's say in the circuit that I had another component in there. Let me put an inductor in there. Some arbitrary value inductor. So let's say we go back to the original schematic. And let's say just be above the C1 here, I put an L1, and we'll use some arbitrary value of, we'll use 1 Henry, okay? Now, I don't want any absolute numbers. I don't need any actual numbers. But what's going to be unusual about the answer to this problem if I have an inductor in there? So with that, it'll have 2 solutions. What we'll have is we'll have a resonant circuit, but we'll have 2 values of capacitance. One will be above resonance and one will be below. That'll give us the same voltage across our resistor. And that's a problem I always like to give my electronics students. I give this one and I'll throw an inductor in there. So then they say, there's 2 answers to this. Yes, there are. So obviously, if we tune it, we don't want to be on resonance, because what do we know about a resonant circuit, a series resonant circuit? What's the impedance of a series resonant circuit? 0, okay? So it's not going to do us any good to have that at resonance. So we actually either have to run it highly reactive or run it off of resonance here. So you learn a lot of physics by actually building this sort of stuff. I always encourage my students to actually build this stuff and test it. It's one thing to sit here and look at a bunch of stuff on screens, but to actually put this thing together, you know, nothing can give you better insight into the actual physics on that. Any other particular questions? Yes? No, I am going to be working on that, though. That's what I start with my little tables here. So I will be doing that. So thanks for reminding me. I'd almost forgotten about that. Do you like this method of doing it? Yeah. Yeah. Anything else? Okay. Well, I guess that should be about it. Thank you for coming out, and let's see. I don't know what other booths are. So I am now working with ARRL with Gordon West, who's ARRL has now taken over the W5YI material. So all the W5YI materials that you've been, hopefully a lot of you have been using, not going to be under ARRL. So do check out the ARRL booth there. Say hi to Gordo there. He's a good friend of mine. I've known him forever and ever. And hopefully take some information home with you. Thank you.